another one. In the atmosphere, 21 volume %. But now, and O is a gas as well. It's one of these nitrous gases. Now it is totally on the left side. This is an example opposite to the other one, totally on the left. So a very long arrow to the left side. And we need 2 NO. When we formulate Kp for this example, what do we have to do? The product is NO, the partial pressure of NO as a gas, but 2 of them so squared, over the partial pressure of nitrogen as a gas. It's only 1, times the partial pressure of oxygen as a gas. Here even it's only 1. Can you please be quiet? It's not needed to stay in here. If you want to talk to your colleagues, please leave the room. Otherwise, please be quiet. It's fair to the other students and even to me. Okay? So here, when we look it up in literature, we find it's 10 to the power of minus 30. Now, the unit for this, what's the unit for this in that example? No unit, because we have bar square over bar times bar square, so no unit in this example. And of course, now we see it's totally on the left because Kp is much smaller than 1. So if we have to figure out, is the reaction totally on the right, on the left? Of course, we have to look into the literature and find out the Kp for gaseous reaction or the Kc when we talk about concentrations. And then we can qualitatively say, okay, it's on the right, it's on the left totally or not, or in the middle. Yes? Well, the constant tells us where, if the reaction is totally working or not. If it is going on one side, if the Kp is 1, it is partially reacting, partially not. So the one way is possibly and the other way as well. It's reversible. If it is 1, and if it is very high, it's totally in one direction. If it is very low, it doesn't work. Yeah. Yeah, yeah. If you look to the first example, hydrogen and oxygen, you have 10 to the power of 80. That is more or less 100%. Of course, a few molecules are remaining as hydrogen gas and oxygen gas, but they can be counted. So in the theoretical chemistry, we never say it's 100%. It's always an equilibrium. And an equilibrium is that what we are describing with a reaction 2 ways possible, but in reality here, energy driven only to the right. Look to that number, 10 to the power of 80. That's very, very, very big. So more or less all is on the right. Okay. And if you want to go back, it is possible. That is what we'd like to say, because I already talked about that last time. What are we doing now in the transition of the energy systems is it's not the only point to install PV and wind power farms and whatever renewable energy power production, we even need some ideas to store and transport energy, renewable energy. And one big idea is hydrogen. But we can see if we'd like to produce hydrogen out of water, that does not work very easy. Therefore, we need to invest energy. Yeah. So if we have renewable power from wind or photovoltaic, whatever, we can use it to push the reaction from the right towards the left side. But that needs, of course, power, because from its nature, it doesn't work like that. It always goes in the other way. But if we push it with power in the other direction, we can do it. And then the positive is we have hydrogen. And when we separate it from the oxygen, we have a chemical, a gas, a compound, which we can store and has quite a lot of energy in. That's the point, no? Because electrical power, we can't store directly. We just can transport it in the grid, or we can transform it into a battery. So it's another form of chemistry needed for charging a battery, or pumping water up the hill, or whatever. It's always a transformation. And one idea is to transform it into hydrogen, which is a storable compound for long term, and we can transport it. But it needs energy, of course. Therefore, we can use electrical power in the electrolyzer. So there is one other example. Now, what we were talking here about is a so-called homogeneous equilibrium. Homogeneous means all of the reactants, yeah, they're all in the same phase. Even here, they are all in the same phase. So that's a homogeneous equilibrium. All partners in the reaction are in the same phase. And you could imagine when we talk about homogeneous, heterogeneous exists as well. So here we have more than one phase. Do you know an example for a reaction where we have a heterogeneous equilibrium? We already talked about one of them, or maybe even more. Do you have an idea? Again, sodium? Yeah. Yeah. Yeah, very, very good, very good. Another one is the combustion of coal. Coal, you know, coal, carbon, pure carbon is coal, solid. And when we burn it, we need oxygen. And what's the product? Carbon dioxide. That's a gas. And this is a gas. That the carbon itself, it's solid. So here we have an equilibrium which is heterogeneous, because we have solid, gas, and gas. If we have an example for this, the Kp has to be calculated in a little different way, because we cannot calculate a partial pressure of a solid material. We just can calculate the partial pressure of a gas. So we say, okay, then we don't need it. We just need the partial pressure of the two gaseous components. And this is CO2. So the partial pressure of CO2, it's only 1 over the partial pressure of oxygen. Those are gases. So for solid components, we have no partial pressure. Solid components, no partial pressure exists. So we do not have to calculate. Well, there are a few more examples. Maybe some of you already heard about the so-called boudoir equilibrium. Boudoir. It's French boudoir. So 24, 25. So the boudoir equilibrium. This is important in the steel industry because we already talked about what do we need to create steel out of iron? Carbon. We need carbon. And for heating up the iron to get a liquid form in this carbon is used, and even for the reduction of the iron oxides to reduce elementary iron, carbon is used. And in addition to that, it's very hot in this process, more than 1000 degrees Celsius. And we have carbon, and we have carbon dioxide from the oxidation of the carbon, but at a very high temperature. So we have partially solid carbon, and we have CO2, which is a gas. And this is the so-called boudoir equilibrium. It can react to carbon monoxide. But then we have C and CO2, we have 2 carbon monoxide. And normally it is totally on the left side, but at very high temperatures, it can be on the right side. It's again the same. It will never react by itself, but when we push it with energy, in this case, high temperature, we can, of course, produce CO from the left to the right in this example. It is a redox reaction. Let's start to talk about that, which is another topic later on, but we already know what is the oxidation number of pure carbon in its elementary form. the oxidation number of pure carbon in its elementary form? 0. What is the oxidation number of the carbon in here? +4. And what is the oxidation number of carbon here? +2. So what happens to this carbon when it's transformed from 0 to +2? It's oxidated. And this carbon from +4 to +2, it's a reduction. So one is oxidized, the other one is reduced. So we have both options in general, because here we have 0 is the oxidation number, +4, because the oxygen always has -2, but 2 times -2 is -4, so +4 for the carbon, and here -2 and +2. So this one to come over here, this one is an oxidation. And that carbon, in the same way, one of them, that's a reduction. Because we have 2 different CO molecules. One is coming from the pure carbon, the other one comes from the CO2. That is a redox reaction. Yeah, we'll talk about that later on in more details, but we need it already now. And here it's an heterogeneous equilibrium, solid, gas, gas. So can you help me? What does it mean for the Kp now? What is Kp in this example? Partial pressure of CO by square divided by partial pressure of CO2. Huh? And as already mentioned, normally it doesn't work, because if we have pure carbon and we always have CO2 in the atmosphere because we exhale it and we have 420 parts per million now, there is no reaction. By itself, this carbon with CO2, yeah, it is much smaller than 1, the Kp. It won't work. But at high temperatures, in the steel industry process, more than 1000 degrees, we could have the reaction so that we have the production of carbon monoxide. And that's important in the steel industry. Why? We already talked about carbon monoxide is a very poisoning gas. If you inhale it, you will die, because it blocks the hemoglobin. We talked about that, the oxygen transport. So, of course, the people working there have to be very careful, because that is what could happen at that high temperatures in the steel industry process. So it has, of course, high relevance. Another example. So we talk about calcium carbonate, and we know it could be a reaction to form calcium oxide and CO2. This is, by the way, an example of a reaction we will do in the lab work session in the next semester. For some of you, maybe even later. And that's equilibrium. We don't know exactly. If we don't know, is it on the right or on the left? We just draw the 2 arrows in the same size. We don't know. But that's not what we like to talk about now. Again, here we have a solid. Here we have a solid. And here we have a gas. Now we have 2 compounds which are solid, and only one is a gas. What does it mean for Kp? Only CO2. It's just the partial pressure of the product CO2, which is a gas. Right. So solid partners do not have a modifiable concentration in the reaction. They are not a term in the law of mass action. Solid partners do not have a modifiable concentration in a reaction, so they are not a term in the law of mass action. Let's try to visualize it in a small figure. We have a cube which is our volume where we are looking to. So this is a cube. I hope you can see it. And in the cube, this is the fixed volume. You remember the ideal gas law, PV is nRT. Now we fix the volume. V is fixed, exactly the volume of this cube. And what we have in there are, for example, we have one solid component. And this solid component is here some particles on the ground of our cube. So this is here, that is a solid component. And then we have, let's say, two different compounds which are a gas. Here, the green one, and they are homogeneously placed in the cube. And let's say this is our product. So here, this particle is a product, that's a gas. And we have another particle, blue, or molecule blue, which is a gas as well. And they are another educt, but they are now a gas. So we have a solid black one, we have a blue dot, which is a gas, and we have a green dot, which is a gas as well. And there is a reaction to the right. We don't know, is it totally or not? But the only thing which could be calculated is on the one side, the partial pressure of these blue molecules and the partial pressure of the green molecules, which are the products. The partial pressure of the solid here doesn't play any role in related to the volume of the cube. So we don't have to calculate it. Well, in general, again, when we have our reaction AA plus BB forms C plus D molecules, and we say temperature is constant, then we can say Kp is constant. Because if the volume is constant as well, Kp is constant. That means, again, we have the concentration of C to the power of C times the concentration of D to the power of D over the concentration of A to the power of A times B to the power of B. But when now C and D, when this is constant at constant temperature and volume, but we have more product, and this is increasing, that automatically means even here it is increasing because Kp is constant. Well, we have a few options to influence the equilibrium. To say, okay, we'd like to have it more on the right or more on the left. We have an idea. What can we do when we look to a reaction? What are the parameters which can be changed to have an influence on where the reaction is? It is on the right side, on the left side. For example, let's look to well, one of those examples we had before. Let's say here, now we know nitrogen, oxygen forms NO, but not really easy. It doesn't work because Kp is minus 10 to the power of minus 30. Look to this equation. What can we do to increase this number? Or to have an influence on that reaction? Yeah. Raising the temperature or changing the temperature is one idea. Yes, very good. Again, changing the concentration. Yeah, if you add a lot of nitrogen, for example, then of course it must even increase here. That is the same, but here's more. Then even this must increase because that is a fixed number. So if you have a reaction where you have two different educts, one is expensive and the other one is very cheap, and you like to have a more or less total reaction to the right, what can you do? You add more of the cheap one to push it in the way that the product is produced, and that all of the expensive is more or less on the product side. Yeah, this equation not because all of them are in the gaseous form. If you have different forms, maybe it helps. But the partial pressure can be. So adding more nitrogen means the partial pressure is increased. Just increasing the pressure in total, that works on all the different components. So that doesn't change anything. But here, adding more nitrogen, the partial pressure of nitrogen is increasing, then of course it helps. So let's note how to change the equilibrium. Change or to influence. Well, one is changing temperature or energy supply. Well, we had an example. We know the way of the reaction backwards. If you have two water and if you want to produce hydrogen and oxygen, normally that doesn't work. It's totally on the left side. That's the vice versa reaction we already had. Now here, when we add energy plus energy, that helps to push it to the right side. Then we can add a bigger arrow to the right side when we add energy. Another one is changing partial pressure of one of the partners.